Okay, hi, good morning, guys. So it's week 8, and today we'll be talking about amortization. Some of you maybe haven't caught up yet, as I've seen from the archipelago post. I think that's okay. I'll try my best to make this tutorial as self-contained as possible. So I'll go through the concepts again. So yeah, let's begin. So let me see. Wait, where's my laser pointer? All right. So okay, I've started recording. So a few things on the list. So today I'll just remind you like where we are in 3230, talk about amortization, followed by interleavings of questions. Okay, so okay, wait. Oops, I jumped too far. I accidentally clicked. Let's try that again. So okay, so where are we in 3230? Okay, guys, just a quick exploration. Okay, so we've gone through 6 weeks where you talk a bit about the basics of design and analysis of algorithms, like asymptotic analysis and divide and conquer, right? That's the early part. And then we had 3 weeks worth of randomization. After that, you had your midterms. I hope that went well for you all. After which, last week, lecture went through amortization. So this is where our tutorial is at right now. And then there's dynamic programming, which I think was this week. Okay, so going forward, there's this, I think next week is on greedy algorithms. And these two are like quite similar, like greedy and DP, they are somewhat related. Okay, so these are just design paradigms. So if you're going to next week's lecture, I think it's good to review this week's lecture as well. Okay, then the 2 weeks after, we'll be talking about this topic called NP completeness. And it's rather an abstract topic, but I say it's quite independent of everything. So in case, like you haven't been following at all these 3 weeks, please do still attend these 2 lectures. Okay, so because from my experience, like students find these topics quite confusing, the NP completeness topics. Okay, so the last 2 chapters, I'm not quite sure what Prof. Arnab intends to cover. This is in his list, but I'll just put it here anyway. Then after that, which is your finals. Okay, so this is just a quick overview of where we are in the semester. So, yep. All right, so let's now talk about amortization. Okay, amortization, right? The motivation here is that we are trying to analyze the sequence of operations in the data structure. Okay, so like maybe on a, like you have seen like on the queue, maybe, or in this tutorial later you'll see on a queue, right? You can do things on the queue, like inserting things into it, adding a set of items into it, right? So if you're trying to analyze this sequence of operations, right? So maybe you do like push, right? It's very easy for you to just take the worst running time of each operation and then multiply everything by that worst case. Multiply the number of operations by the worst case running time, right? So what I mean is that maybe, for example, sometimes the operation takes like ON time, right? But most of the time it's O1 time. But if you are pessimistic, you'll take the ON time times the number of time you need to operate on it. Okay, so here's the diagram. Like you might be overcounting. Okay, what if some operations actually take way less cost? Like over here, right? I have an operation that takes like, this is like 8 units of cost, but it only happens once out of like 8 times, So if you are doing the naive one, the worst case running time of each operation, you do like this cost times how many times you need to operate on it. Okay, so this is kind of like the motivation of amortized analysis. So amortization is all about trying to change your perspective in counting the cost of each operation. Okay, like the way you view the cost, you kind of like see it in a different lens. Try to be careful about the way you count. Okay, and you realize that, oh, actually you are counting a bit too much. Okay, so then there's a way for you to ensure that you count everything properly. Okay, so common techniques, there are 3 common techniques used for amortization. Explore in the textbook as well: the aggregate method, accounting, and potential. Okay, so accounting sometimes is called a banker, and potential is sometimes called the physicist. All right, so our goal of amortization is to give guarantee of kind of like the average performance of each operation over all the things that you have done so far. Okay, so a slightly possibly confusing subtlety here is the average case analysis. Don't confuse it with average case analysis, because the average case analysis is trying to analyze the performance of your algorithm over random inputs. So like maybe, for example, in quicksort, right, the input can come from a distribution of any permutations of array, right? Then you are interested, hey, what's the average case of quicksort if you're given like, if you take the runtime of like one permutation plus the runtime of the second permutation until all the n factorial permutation, then divided by how many times you run the quicksort, that's kind of like the average case analysis. In amortization, there's no randomness, right? So you try to average over the total cost of all operations, and this is the worst case. Kind of like you analyze, you carefully count, like in the worst case this happened, in the worst case sometimes the expensive operation happened. Okay, so hopefully this clarifies a little bit. If you need me to mention this again, please let me know. Okay, so aggregate method, we won't discuss it in the tutorial. I think it's not as powerful as the other two, like accounting and potential method. They are usually in 3230. If we ask for amortization questions, we'll say using the accounting method, show that something. Using the potential method, show that something. So aggregate method, we don't really use it as much in 3230 from my personal experience. Okay, so accounting method, let's quickly talk about it. What about it? So here's an analogy, right? Living expenses. So I hope I didn't have time to double check my example, but later on I hope there's no bugs in the example. Let's try. So analogy here, like one I came up with, is my living expenses. Okay, so let's say, right, you have some daily allowance, like $15 of allowance. Okay, so every day you need to spend a bit, maybe like for food or for other needs, right? But let's say every day you don't need more than $10 on food, for example, maybe. Okay, so but because you only need at most $10, right? You also can set aside some money every day, right? Set aside some money, and then this money is okay. Wait, some money, right? Like $5 here. It's kind of like you save it for rainy days. Okay, you kind of like save it. And at the end of the month, let's say at the end of the month, somehow you have to pay rent for like $120, and I'm fully aware rent is not this cheap. Okay, so this is just an example. So if you think about it, at the end of the month, if someone tells you, hey, you need to pay $120, and then you consider your daily allowance, right? If you consider purely on your daily allowance, perspective of daily allowance, it's definitely way more expensive compared to your daily allowance. Okay, so but the good thing is that you set aside some money every day. Some money every day. So you kind of like save enough so that you're able to pay for a possibly expensive thing when it comes. Okay, this expensive thing, like the rent, only comes maybe like once a month, right? It's not every day you need to pay $120. So you kind of like set aside some money every day ahead of time, so that in the future you're able to pay for it. Okay, so if you now think about it in the perspective of your daily allowance, right? With respect to your daily allowance, the rent of $120 is kind of like double quote cheap in the sense that maybe all of your savings paid for it. So you took nothing from your daily allowance of that day. You took nothing from your daily allowance of that day to pay for the expensive rent. Okay, so it's cheap in that sense. Okay, because the you in the past decided that, all right, so let me pay for it. Okay, so the you that is today, right, it says, oh, my daily allowance is still $15. I can still do whatever I want with $15. Okay, so hope this analogy somewhat makes sense. Let's try to see an example very soon. So the idea is that you want to impose an extra charge on inexpensive operations, right? So and use it to pay for a later expensive operation. So you be generous, you know, like you ahead of time the operation that's supposedly cheap, you say, actually, you know what? Let me be a bit more generous and say that, okay, I'll pay a bit more for you, but hey, help pay for a future expensive operation. Okay, so charge IF. So there are some notations coming in. So charge IF operation are fictitious, right? So this is amortized cost CI, sorry, where $1 is a 1 unit of time. So the analogy here, the amortized cost is basically a daily allowance. Okay. Then the amortized cost will be used in two ways. Your daily allowance will be used in two ways, right? One of it will be used to pay the actual cost, denoted as TI, right? The analogy here is that this is the daily food, right, that you have to pay for. Okay. And then you also separate it into a portion where you store it in the bank. So the analogy is that you're setting some money aside. Okay. So basically, when the expensive operation comes, use money from the bank instead, or like a good portion of the money from the bank instead. Okay, so paying the rent with savings is kind of like this expensive operation that you pay from the bank. Okay, so here's a scenario, right? So you just started life, you have no money in the bank. So take some time to quickly see the table column headers. So I have day, actual cost, amortized cost, and how much you kind of like put in the bank. Okay, so here's the bank. It starts off with $0. I'll update that as that goes. So let's say in day one, you bought some chicken rice, okay, $10. So actual cost of that day, right? Actual cost of maybe operating with the data structure is 10 units, $10, okay? But your amortized cost, which is your daily allowance, is 15. So you save 15, you decide, okay, let me put $5 in the bank, okay? So $5 in the bank. Day two, you try another food and it also costs $10, right? So same thing, actual cost is $10, amortized is $15. To the bank is 15 minus 10, which is 5. So now the bank has $10. And so on, okay? So, okay, here I just want to emphasize, right, that sometimes the actual cost of different, it doesn't have to be consistent throughout. Maybe the actual cost here, like one of the days is $5, for example, right? So this should be day 3, not day 2. Daily allowance is $15 still, right? You decide, okay, your amortized cost, let me put $15 still. But that means I'm able to save more at $10 daily. And so on, right? This process keeps going on and going on. So let's say a lot of things happen along the way, but at the end of the 30th day, you have $150 in the bank. Okay, you have $150 in the bank because like all of these accumulate to 150. Okay, I didn't tell you like how what happened in between. So let's just pretend at the end of the month you get $150. Then the rent payment comes. Okay, $120 rent, right? And you still need to buy food for $10, for example. Okay, so the actual cost is 120 plus 10. Let's say. But definitely you cannot pay your daily allowance. So you take some money out of your bank. So use the saved up money to pay for the rent, like 120 versus 150. And you realize, okay, I have still enough money in the bank. I still have $30 in the bank. And now the rent is cheap, right? Because now you don't need to pay anything of the rent from your amortized cost. Okay, so just focus on today's expenses. Then, like usual, this $10 is paid by the $15 here. Okay, so that's to the bank. Okay, so in total, right? In total, let's say the 31 days here costs like, okay, so in total 430 and 465. Okay, yeah. So here, what I'm saying here, suppose 31 days is like the actual cost and the rent is $120. So adds up to 430 and amortized cost is 465. Okay, what you notice here, right, if you sum up, at all points of time, your amortized cost is always upper bounding your total actual cost, right? So total actual cost, you only care about the amortized costs, right? And you see that, hey, actually it's 465 units, okay? But this is provided that the bank never goes negative. So this is something I haven't mentioned throughout, but it's important that the bank amount never goes negative, so that at all points in time, the total actual cost is always upper bounded by the total amortized cost. Okay, so this is the formula, right? So if total amortized cost, why do we care so much, right? Because if the total amortized cost bounds this thing, right? So let's say like an easy way to look at it, because let's say this is like sum equals ON, right? So if this is equals ON, right? Because it upper bounds the true cost, it also means that this true cost is also ON by transitivity. Okay, so this is why we care about this upper bound. Okay, so okay, I spent quite a bit of time talking about accounting method. So let's just go through the questions. Okay, 3 minutes I think is too long. So let's quickly hop in Archipelago and try to put some answer. So maybe a minute or two. If you are confused, please let me know, because that'd be bad. So resume around 9:22. Okay, so how many people answered? Okay, so 15 people has answered. We have 21 people. So okay, not so bad. That's a relief. No one is answering that you don't know what's going on. So we're quite sure the moment I say that it appears. Okay, I think like most people has answered. So in the interest of time, because the more important questions are behind, let's go on first. Okay, so option A, right? The amortized cost for insert in dynamic table is $1. Is theta1. Okay, this is true because what you can do, right, is charge an amortized cost of $3. Okay, so remember, this is like the thing that you divide into two. So $1, use it for the actual insertion, and then $2 to the bank. Okay, so here's an example. Like, let's say we just double the table. This is the current situation. We have some room left. Okay, and just a note here, I'll ignore the cost of allocating and deleting elements, only count the cost of inserting and transferring. Okay, this is just for demo purposes, but it doesn't matter. Even if you include it, you can just change the constants a bit. Okay, so let's say we just double the table. Let's say we insert 4 more times, right? We insert 4 more times. Insert. Every one of them costs $3. Every one of them costs $3, but $1 is used for the actual insertion. And then each of them, you store $2. Each of the element has $2 associated to it. Okay? So when we insert one more time, we actually need to double, right? We need to double. So let's say the creation of the table is free. Let's just say for demo purposes. But again, as I want to emphasize, it doesn't matter, right? Because the cost, you can just tweak the constants as required. So the cost of transferring, right? There is a cost of transferring. And this cost of transferring, if you transfer the first 2 elements, it is paid for by one of the elements here, one of the elements that you just inserted. So an element that you just inserted pays for 2 of the entire array. So like this guy is paid for by this guy. And I hope you can see that like the next 2 is paid for the next guy. The next 2 is paid by the second last guy. And finally, like the last 2 is also paid by the last guy. Okay, so yep. And then finally you do the actual insertion, which gives $2, which gives $2 associated to it. So yeah, hopefully you can imagine like this. Why we need the $2 is because you pay for the transfer of the previous guys as well. Okay, so amortized cost is O1 is $3. And option C, right? So suspiciously, I skip option B. So option C is true because okay, here is notation. He used something different. CI is an actual cost, and C CI cat or CI cat cap or hat CI hat, right? Is the amortized. So remember the amortized cost is always an upper bound. The total sum is always an upper bound on the actual cost. And then total amortized cost must be larger than the sum of actual cost. So this is true. Okay. I don't know what much to say. This is just by definition. Okay. But option B is false, right? So at any point in time, right, the single amortized cost, it can be smaller than the actual cost. The entire point of us doing that additional payment is so that we are able to defend against like the single time that an expensive operation comes. Okay, so insertion example here, for example, right? Our amortized cost is always $3 to insert, but the actual cost is actually more than $3 because you probably need something like, hey, you need to copy 8 elements and then you need to actually insert the element, and that's definitely more than $3. Okay, so hopefully for those at least who did not choose this option to be false, you have a better understanding now. Okay, so any questions? Okay, if not, let's go to the next example. So next example, we have a queue data structure. Okay, and the queue data structure, it supports a few more operations compared to usual. Instead of the normal NQ and DQ, you're also deleting, there's this operation delete K, which is dequeuing K elements from the queue. Either that or you add a set. A is a set, and queue all the elements in A. And Q, DQ, delete, add. Okay, so here's a visualization, right? So you start off with an empty queue, right? If you NQ, just do normally. I think this should be covered in your 2040 and stuff. But this is a new operation specific to this this tutorial. Let's say we add a set of items 2, 4, 6, 8. So in a single operations, it went from 18 to 18, 2, 4, 6, 8. Okay, so adding things. And then there's also delete 3, which is saying, hey, pop or like DQ 3 elements. Okay, so this is delete 3 and then DQ, right? So I think the operations are pretty intuitive and simple. And the claim is that all of these things, NQ, DQ, and delete runs in amortized O1 time, while adding the set of item runs in amortized the size of the set. Okay, so the cardinality of A. Okay, so using a counting method, try to prove these time complexities. And in order for you to use a counting method, you need to state the charge. Okay, the charge here is the amortized cost. So tell me, how many dollars are you charging every single one of them? Where does it go to? Okay, so let's give you a bit more time, like around 2 minutes in Archipelago. Might take a bit more time to type. So 9:20. Let's resume at 9:29. Okay, nice. Okay, revisiting the question on like which part need more clarity. A lot of people are confused by potential method. Okay, so yeah. Okay, it's 9:29. So I'll just go on first because I see a lot of people confused about potential method. So I like to maybe talk about it in the next section. And I think this section is relatively still okay, accounting method-ish. Maybe just formalizing it will be tricky the first time if you haven't done it before. Okay, so question 2 idea, right? So here's the important bit, right? Why we need the amortization? It's because the deletion, right? Naively, if you think about the normal deletions, right? It usually takes okay time. Okay, if you delete 10 elements, you take time like 10, for example, right? But now we want it to be amortized O1 time. It means that you try to pre-charge other operations, try to pre-charge the other operations, right? NQ and add, for example, right? Such that the deletion is kind of like free. You pay in advance for deletion. Okay, so here's the proposal. So for every NQ, and I think a lot of you got it right, so that's great. So NQ, right, for every NQ, charge $2. So this is the amortized cost, $2 amortized cost. So $1 is used for the actual insertion, for the actual pushing into the queue, right, NQ into the queue. But you store $1 in the bank for a future DQ. And the idea here is that you save this $1 so that you kind of like, hey, let me pay for this DQ on me in future. Okay, so for the future DQ. So adding a set of elements 2, 4, 6, 8 is charging $2 times the number of elements. Okay, so same as before, because it consists of the size of A and Qs, each charge $2. Okay, each of them charge $2, and then $1 for the actual insertion, right? $1 for the actual insertion and $1 in the bank for each and every one of them. Okay, so deletion, right, is basically free. You can just say, hey, amortized for deletion is 0. Okay, why? Because the actual cost, which is like 1 for each of them, K, right? There are K of them, is already paid for already by the insertions. In order for you to delete all these things, you need to have inserted them first. Okay, so key elements deleted with K dollars from the bank. Okay, so I'll pause here if anyone has questions. This is the kind of like the key point of the question, trying to make this cheap, or at least argue that in the amortized sense, deletion is cheap.
So can we always assume that data structure will start from empty?
Okay, that's a good question. So yes, so the initial state of data structure. So the question is like, can we assume that data structure is always empty? So I think it depends on the question. So you have to read carefully what the question wants. In the last question, you start off kind of like with full table, kind of like the other way around. But the point I want to bring about is that it's important to consider the initial state of the data structure as well. So depends on the question. In this question, we assume that it starts off empty. So by right, assignment should tell you like, oh, like the state of the initial state of data structure, what is it? Okay, so if not, then please also try to maybe ask. It can be helpful to ask. Okay, so yep, do consider the initial state of the data structure. Okay, so deletion. Then DQ, right? DQ is basically, well, it's an easy version of delete. So same thing as before, just charge $0. Actual cost is paid for already, right? So just delete using $1 from the bank. Okay, so one final thing to argue, right? And I think it's easy to forget is, does the bank ever go negative? Right, this is an important question to answer, because if the bank ever goes negative, then our argument kind of like falls apart. Okay, so in this case, it's not that hard to argue, because after each insertion of element, you have $1 associated, right? And as I mentioned verbally earlier, when we DQ the element, that element must have been inserted first, right? So there must have been $1 associated to that element first, right? So we are just using that $1 associated with the inserted element, and there's always enough money in the bank. We don't have to like make it go negative. Okay, so as a summary, right, you can see here in the table, right? So NQ, DQ, and delete, all of them cost O1 amortized time. Just charge them like $2, $0, $0. The actual cost might be a bit different. Okay, like $1, $1, and K dollars. So, but the point is that like everything, the sum of US government running out of money. Yeah. Yeah. But anyway, this is the summary. And the point that at all times the bank never goes negative, and your total amortized cost, right? The total sum always upbounds the actual cost. It doesn't have to be that each one of them individually upbounds it, right? As you can see here, $1 is greater than $0. But the total sum of amortized cost has to upbound the actual cost. Okay. One final thing I want to talk about accounting method is that this $2, right? You're being precise, right? Like, oh, pay exactly. The bank will like just nice the money be used. But well, if it makes you easy to think, like sometimes you can overcharge a bit also, just to make your life easier, you know. So if you don't want to think too much, especially in the case of table doubling. Okay, so overcharging is a bit fine as long as it's constant. Okay, so yeah, so I'll quickly go through potential method, or maybe not quickly go through, because I think a lot of people are confused. And I must admit, because I took really long as well last time to understand what is actually going on for potential method. Okay, so potential method, right, is another perspective to counting. And this is kind of like, instead of in accounting method, you're paying in advance by storing money in the bank. Okay, in potential method, you are trying to build up a potential energy, right? So based on the state of the data structure, right, build up some potential, and then once the expensive operation come, use all that potential. So there's this potential function phi. Phi is the potential function associated with the algorithm and data structure. And this is usually not given to you. And this is something that we want you to define. Okay, this is the key step of potential method. You have to carefully define this yourself. So phi of I is the potential at the end of the ith operation. Okay, and delta phi is basically the potential difference from going the I-1 to ith operations. How much did your potential change? Did it increase, or maybe did it decrease? Okay, so this is notational stuff. I'll keep putting this on the upper right corner so that you don't forget. So I give a little chart here to kind of show like what each one of these means. I'm sorry it's not to scale. Hope you can forgive me for that. So phi of 8, right? So this is the ith operation, the 8th operation, 9th operation, 10th operation. So over time, potential might increase, then potential decrease because of something, then it increase for some example. So the delta phi of 9 here, right? Okay, so sorry. Let me talk about the horizontal lines first. So this point here is phi of 8. Phi of 8, which is 10. 10 is the potential at that point in time. The potential difference at the 9th operation, right, is 2 minus 10, right? Because you drop, the potential dropped by 8. So the potential difference is 8. So this is phi of I. And then like similarly, from the 9th operation to the 10th operation, the potential increased by 1. Okay, so analogy, right? So I tried my best to find good analogies, and this is kind of like the best one I could find online and could think of also, is a water tank, right? So when you open the faucet, right, you have some nice pressure, water pressure, let's say for example. But if it's empty, right, if there's no water, if there's very little water, there's barely any pressure. So you try to slowly refill to build up the pressure. So it's kind of like building up the potential energy. Okay, so the potential function is kind of like the water in the water tank itself, because as you fill in more water, right, the potential in the water tank increases. You have more potential. You have more potential to kind of like give a nice water pressure. So if you draw the water out, there will be some nice water pressure for you to get the water, but the potential, because you keep drawing water out, right, the potential decreases over time until there's no more. So drawing a lot of water is kind of like cheap, right? If you start with a full tank, this I know this might not be okay, I'll go on first. So from a full tank, if you try to draw a lot of water, it's kind of like double quote cheap, because that water pressure is kind of like trying to push it for you. Okay, so it's similar to accounting method where you have a stored up energy, right, to pay for the expensive operation. Okay, I'm not too sure whether this analogy helps or it hurts. Hopefully it doesn't hurt at least, but I don't know if it just helps. Okay, so yeah, so this is just same slide as before, just revisiting the notations. So okay, it's 8:39. I hope I can go through. So I want to just quickly show why potential method works. Okay, so why do we care about all this definition? So as before, define amortized cost CI, that is the actual cost, but you adjust the actual cost by a bit. Remember, we are kind of like maybe plus increase it by a bit or decrease it by a bit. And same as accounting method, the sum of amortized cost should upper bound the sum of the actual cost. Same conclusion also. If we have this upper bound, we can say something. If we can say something about the amortized cost, we can also say something about the actual cost. So in potential method, the definition of CI equals to the true cost plus the potential difference. Okay, so it's a long, it looks long and scary, but you can just focus on this rightmost part. It's the true cost plus the potential difference. Okay, this is just kind of like how we define potential method. Okay, so the idea is that if TI is small, right, this is the cheap operation, then we want the change in potential to be positive and small. Meaning, in analogy of accounting method, we have a cheap true operation. We try to assign it some additional charge so that it pays for a future operation. So this is building up potential. This delta phi I is building up the potential. However, if TI is large, then we want delta phi I to be negative and large. This is the analogy of you use up all your money that you have saved in order so that the current expensive operation becomes cheap. So in potential method, if the TI is large, if it's expensive, hopefully by then we have enough potential so that we can just drop all our potential, right? Make the potential negative, the delta, right? So the important bit is the delta, the change is negative, it drops. And then this is large enough so that it cancels off the TI. So that CI is also small. And recall CI is the amortized cost, C is the amortized cost, T is the true cost. Okay, I hope you don't get confused in notations here. Okay, so an important bit is that something I didn't mention earlier is that the initial state, the phi 0 equals to 0. And this is like where Daniel's earlier question is important. The initial state of the data structure is important because a different state of data structure can give you a different initial phi. Okay, so that is what you want to argue here. Phi 0 equals 0 and phi I is more than equals 0. Okay, so okay, warning ahead, right? Math. So I'm gonna see a little bit of math. Okay, so we want to show that the sum of amortized cost is upper bounded by the sum of the actual cost. So here I have the sum of the amortized cost on the left hand side, and then I substitute my definition into here, into CI basically. This is by definition. In the next line, I expand the sums. Okay, so TI, this is like Tn plus phi n minus 1 plus T. Okay, I don't want to say all that out. This is basically me expanding all the sum. Okay, then in potential method, if you notice this pattern, this is something what we call, it cancels. This is what we call telescoping. Okay, so diagonally they cancel except for these two terms, phi n and phi 0. Okay, so they cancel off. And then basically you can still sum up over all the true costs, right? So this is what we wanted on the right hand side, sum of all the actual true costs plus phi n minus phi 0. So copying over from the previous slide. Okay, so this is what we have before. Okay, so the next step is that, remember we wanted our phi start off with 0. So this guy just cancels, just becomes 0, minus 0. And phi I is greater than equals to 0. Okay, so phi I greater equal than 0 means we can like bound this thing. Okay, so now we know that the sum of amortized cost is the sum of actual costs. This is all this math is why we define our potential method the way it is. All the deltas, all the phi I, this is why we define it in that way, so that we are given this, we can have this bound. Okay, so we show that the sum of amortized cost greater than sum of actual cost is shown, and we conclude, right? Since one upper bounds the other. If the sum is O of some Fn, then this thing that it upper bounds is also O of Fn, similar as before. Okay, and now we bound the total actual cost for free. Okay, this is what I said, right? So the strategy for potential method is usually to try to select a suitable phi so that for a costly operation, the delta phi is negative, that it cancels off. So I took this off from the lecture slides. And the advice given in the lecture is you try to view carefully the costly operation. You see there's some quantity that is decreasing during the operation. Okay, so the question you have in mind, like, oh, when to use accounting, when to use potential, we usually tell you what to use. It can be either one. Choose whichever you find more intuitive. Okay, some people find one easier to use, and some think like accounting is easier to use. Personally, I just prefer the accounting method. Yeah, I found potential method slightly difficult to reason about, but I heard it's pretty powerful. It can be used for even very complicated data structures. Okay, so I hope that was enough time, like enough elaboration. So especially those who ask like to elaborate on that, I hope it's clearer now. The third question is same as before, question 2, but use potential method. So I don't know if we have time for archipelago, but just give it a quick, I'll give you a minute to think about it. If you still don't understand, please put you don't know in the archipelago. So I hope I can slowly go through, because it's 9:45 and I still have 2 more questions to go through. Okay, so I'll just wait for like a minute or so. Okay. 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 So okay, I will go through, and if you have any questions, let me know, because I think some people are, at least I think they seem to understand potential method better, but still need time to digest and apply. Okay, so remember, we want our delete is the thing that is costly here, right? Deleting k elements is the thing that's costly here. We want it to be cheap. So to define our potential method, we see what we want to kind of like nullify, what's decreasing during this expensive step. Okay, what's decreasing during this expensive step? This is, if it's pretty clear, like you remove things from the queue, means like the number of elements in the queue, that's the things that's decreasing. Okay, so phi I, this is what we choose to define as the number of elements in the queue after the IF operation. This is what a lot of you actually put in the archipelago. So that's really good. So for NQ, right? So let's go through this single example. We argue that everything has amortized cost as needed. So for the NQ step, the actual cost is TI, which is 1, right? Which is just 1, just NQ it, actual cost. But in terms of the potential method, remember we want the amortized cost is the true cost plus the change. Okay, so we have one new element, phi I minus 1. The change in potential is basically 1. So even if you have like 5 elements at first, in this step now you have 6. So the phi I, the delta phi is 1. So the amortized cost is the actual cost Ti plus the change in potential 1. So 1 plus 1, I get amortized cost of 2. Okay, so amortized cost of 2. Okay, so this is by definition. The next step for DQ is similar. Okay, so it's similar, but I have 1 less element when I DQ. So the change in potential, the delta phi I is -1. I remove 1 element. So the amortized cost is 1 plus -1 instead. I get 0, similar as before. For deleting k elements, I now have k less elements. So this is -k. And the actual cost is actually k. And this is the important bit, right? This is what we wanted to argue for. The actual cost is k, but we have enough potential build up over time so that Now I can use up the potential. I use negative K potential. So K plus negative K, then it is 0. So now the deletion is kind of like free. Okay. So for adding, similar. Okay, I won't go through long for this. So remember, you have to fulfill these additional properties. Phi 0 equals 0, phi I is more than equals 0. So number of elements in the queue. So to argue this is very simple, right? In the beginning, we have an empty queue. The state of the data structure is important. So phi 0 equals 0, and we never have negative elements, right? You can only have like more than equals to 0 elements. So this is also easy. Okay, so anyone found that confusing? Because the next question is also about potential method. So hopefully that wasn't too confusing. Okay, I might just end on time, like at 10, because the last question is pretty important. I might have spent a bit too long accounting, but yeah, so dynamic table, delete only. Okay, if there are no questions, I will go through this question now. So the idea here, right, you have the dynamic table, but you start off with a full table. This time you start off with a full table. The state is important. Once the number of elements is half, right? So you can ignore all these parts, I guess. You delete the last element, the number of element is n. And then once the table size is half of like the actual entire capacity, the entire size, you create a smaller table and copy it to it. Okay, so this is what this pseudocode is saying. If the elements is half the size, it can hold. Let's just shrink it. Okay, so show that the amortized cost of this operation is O1. Noting that we do not call any other operations on T. Okay, using potential method. So I'll just give you a minute to just stare at the question. It's okay if you don't understand. It's a bit trickier to define. Okay, so 9:52 resume. So sorry, I'm rushing this part slightly because didn't expect the accounting to take that long. Okay, do put in archipelago. It's on, right? Okay, it's 9:52, but I see very few answers. So are people very lost for this question? Okay, sure. I see some answers. If you don't know, just put you don't know. Okay, Ken. So let's yeah, okay, Ken, don't know what's going on. Oh no. All right, so let's try. I'll try my best. So if you have to leave, this section is recorded as usual, but because people are confused, maybe it's worth going through this more slowly. So sorry, like tutorial slightly over timing today. So the idea is that there are two possibilities when you delete, right? So you just delete normally, table just doesn't shrink, you just delete it. This is cheap, right? So note that this is the size of the table. This is the entire size of the table, and n is the number of elements. Okay, n is the number of elements. So you start from like 8 elements, becomes 7, but the size of the table doesn't change, doesn't shrink. And case 2 is that when the table shrinks. This operation is the expensive operation, right? Shrinking because you have to copy things over. So not only do you delete this, you have to create a new table and then copy it over, copy elements over. The size decreases. Okay, so 2 cases to consider. Okay, so as before, we try to find a decreasing quantity during the expensive operation. This thing is expensive, right? This thing is expensive. So what is the thing that might decrease? What's a candidate potential function? Okay, so there are two candidates here that are actually decreasing. Okay, first one, which actually the initial one that I thought of, is the size of T. The size of the table is decreasing. It shrinks, right? It shrinks. It's quite clear because the table is shrinking, so the size of the table shrinks. So that's the potential function that I want to propose. Okay, but if you think about it a little bit more, remember we have this condition, phi 0 has to be equal to 0. But because we start off with some non-empty table, we start with the size of 8. If we define size t to be the potential function, then the initial state, phi 0, is like 8, equals to 8, which is not 0. Okay, so this is the condition that we want to impose on potential method. So size t is actually not a good potential function, or at least it doesn't satisfy this condition here. So here's an alternative, size t minus n. Okay, but size t minus n, if you're still processing what size t minus n means, it's the number of empty slots in the table. Okay, so like here I have 3 empty slots. So it's decreasing over time because initially you have a lot of empty slots, right? The upper half has a lot of empty slots. But when you shrink the table, there's no more empty slot because you fill it up. Okay, is this potential function clear? Okay, so please give me some thumbs up, maybe. Yep, thanks a lot. Okay, nice. So I see thumbs up, thumbs ups. Right, so size t minus n is the potential function here. So, okay, again, you verify that it satisfies these properties, but if you think about the number of empty slots, initially a full table, there's no empty slot. So it satisfies the first condition. And over time, well, number of empty slots never negative. So safe, we are safe. Okay, so now let's analyze the two situations, right? We want to argue that amortized cost of them is O1. Remember, amortized cost is the actual cost plus the potential difference. Okay, so in the case that table doesn't shrink, the actual cost is 1. Because all you need to do is delete the element, right? The delta phi of I, the change in the number of empty slots, is 1. Okay, you can verify with this formula, but again, think about it in terms of empty slot. Here, we start off with no empty slot, and then over here, we have 1 additional empty slot after deletion, so 1. The amortized cost is the sum of it, which is 2. 1 plus 1 equals to 2. Okay, so okay, so this is the easy case, right? Table doesn't shrink. Okay, any questions about this particular one? So I'll stop at this for like 10 seconds if anyone has questions. Okay, so the next question, the next case is the table shrinks. This is the part that we want to argue. It's actually cheap. Okay, so this operation is expensive, right? Because okay, for simplicity, right? N here is just with respect to the final number of elements. So this is n plus 1, and this is 2n. Okay, so this operation is expensive. We want to argue that the amortized cost for this is actually cheap. So actual cost is something like n plus 1. You need to delete this last guy and then copy the first n guys here. Actual cost is n plus 1, and then copy the rest. Delete 1 and then copy the rest. Okay. What about the change in potential? The change in potential is 1 minus n. Okay, so well, it's basically like this guy, 1 minus n. You take from having this much empty slots, it suddenly becomes 0. Okay, so I did the math here in case like you're not convinced. The potential before is 2n minus n plus 1, which is n minus 1, and then potential difference is 0 minus that guy. So if you're not convinced, this is the math, but trust, if you are still confused, just trust me on this. This is a change in potential. Okay, then the amortized cost, you sum up these two things, n plus 1, the n cancels off. The key here is that the n cancels off. The way we define the potential is that it just nice drops enough potential to cancel off the expensive operation. Okay, then 1 plus 1, we get 2 for the amortized cost. Okay, any questions about this one? Okay, if not, then this is a summary of what just happened. This is our potential. This is the number of empty slots. Case 1, we shrink the table, right? Amortized cost is 2. Case 2, case 1 is that we didn't shrink. Case 2 is we shrink. Both of them have amortized cost of 2. So the amortized cost of this entire deletion, right, is O1. It's constant. It's 2. Okay. So just to remind you again, right? So what amortization is all about is trying to change your perspective on what you're counting during each operation. At the end of the day, right, they're just kind of like tools. I know like I kind of like gave a step-by-step how to use them and all, but try not to be too hung up on following the recipe. They are kind of like guidelines. You can be creative as well with the way you amortize things. As long as it makes sense, I think it should be fine. Okay, so I've seen some pretty creative amortization schemes as well. So yeah, so try to think like how you can assign the costs carefully so that things add up nicely. Okay. So wrapping up, so tutorial and lecture examples, I think they are still relatively simple examples of amortizations. Like usually it's pretty, okay, I won't say obvious lah, but I say these are still pretty relatively basic examples of amortization. But that also means that you might not see the full capabilities of like these two techniques, how powerful they are. So like for those of you who are interested to explore, these are some possible things you might want to explore. There's this thing called the scapegoat trees, Fibonacci heaps, 233, 255 trees. You don't have to know this for this module, of course, but in case you want to see more fancy examples of amortization, do explore these examples. There's a supplementary MIT lecture on amortized analysis in case it's still not clicking to you. But I want to warn you that they go through one additional method that is not in the textbook, which proposed by the prof. We might not recognize it in 3230, but if it makes sense, I don't see why not TBH. But again, good to have supplements. But just note, right, this lecture, it goes through an example called the 233s, which is gone through in another of the MIT lectures. So they kind of expect you to know that in case you are visiting this lecture. So I link it here as well. Okay, so thanks a lot for coming today. This is all I have for you. Let me share the slides in the Zoom chat. Copy link. Okay, so that's it for today. Wait, sorry, I haven't unlocked it yet. My bad. Okay, try again. I hope the link, I think the link is still the same. Yeah, the link is still the same. I think, okay, nice. Here. Okay, so that's all I have for you today. So a bit over time, longer than usual. I didn't expect that. If you're still confused about the potential or the accounting method, do let me know. I'll just stay back for like 30 more minutes for consultation and so. Okay. Thanks a lot, guys. No problem. No problem. No problem. Do you have any questions?
Oh yeah, I have a quick question.
Yep.
Yeah, I think questions two is it? I think question two, the one about the NQ, DQ, all that, right?
Sure. Yeah.
So we assign NQ like a charge of yeah, you charge it $2, right? Then delete delete and DQ because there are operations that remove that remove an element from the data structure, right? We charge it $0 because we say that whatever it actually costs, it can be paid for by amount from the bank, right?
Yes.
So if you want to write it in a proof, right, how would you write this actually?
Honestly, this is exactly how I will write it in the proof, actually.
Oh, then how would you I mean, because you charge it $0, how do you justify that is some that the cost is of 001?
Okay, I mean $0 is kind of like upper bounded by a constant. As in,
Okay.
I know it's kind of weird, right? But zero is something like we don't normally talk about in time analysis, right? But
Yeah.
I mean, even if you think about it in terms of in terms of the graph, right? 0, okay, let's say 0 is over here, right? Not the usual origin. Like, let's say even if it's 0 throughout, it's still upper bounded by
Like
some
1 or something.
constancy. Yeah,
Okay.
by 1, right? So it's still fine. Yeah.
Okay. Okay. Makes sense.
Yep. So usually this is what we do. So yeah, I think in my past assignments, this is exactly how I do it also. Like I list down every single one of them. Oh, NQ, I charge $2, $1 go to the actual insertion, $1 goes to the bank. Then I argue that the bank never go negative. So this is the crux of why amortization, the accounting method works.
Okay.
Hmm.
All right. Okay. I think that's all for me. Thanks.
All right.
All right. See you. Bye.
See ya. Maybe I should.
Actually, I don't have much. I just wanted to check the Could you run through like the potential method part for question 4? Like it's fine around here. Yeah, like Tn. You say it's Tn. Wait, what was that? T minus n, right? Something like that.
This one is it? Yep.
Yeah. Then how will the potential? How will the potential? Could you run through how the potential will change? Like phi delta phi will change. Yeah.
Okay. So if I understand your question right, this is my potential function. Then you're asking how the delta changes, is it? Right. So the delta here, by definition, is change of the change of potential function after the change of the potential after a particular operation. Okay. So if you think about it, right? If I plot this in a graph,
okay,
the initial state is something like this, right? The potential initially start off with 0 because the table is full. And the number of empty slots is 0, right?
okay, yeah.
Okay, so the important bit, okay, if this is confusing you, just think of it as the number of empty slots. Okay.
So technically this will like increase
Yes.
until it hits half and then it just crashes.
Yes. So the graph might look something like this. So increase by 1. This is 1. Then increase by 1. Increase by 1. Then hey, it will drop to, okay, maybe increase a bit more. Then drop to 0. They increase again. Then drop to 0. Then increase again. Then drop to 0. Something like this.
Okay, yeah, it's just lagging. Okay.
Oh yeah. Sorry. I think I connected the yeah. So Zoom doesn't show unless I release. So the potential looks something like that. So it increase, then drop, then increase, then it drop. Then the key bit here is that the delta here. This is the delta, right? This is delta. The delta is like how it changes, how it is based on the potential function. In this particular example, my delta is like either 1 because I increased the empty slot by 1, or like I think n minus 1 if I'm not wrong, and that comes from all this drop. So maybe this was like let's say initially like I have
size t over 2 minus 1 or something.
Yeah, it's okay. I don't want to do the math because but you can try. But basically this is okay. I think I have this example here, right?
Okay, I think I roughly
Yeah.
how it works.
So this is basically how many empty slots here. So this is this point. Let's say this is okay. This is three slots, like for example. Let's ignore this axis. So this is 3, right? Then suddenly it becomes 0.
See how it works. Then how would you formalize this? Like you say, okay, now we have this delta, this thing that works, right? So how do we show like?
Usually for I mean, because we recognize potential method, I would say all you need to do is state the potential function, right? State the potential function, and then argue that well, the amortized cost of each one of them.
So we
The
can just like
amortized
someone
cost-
draw this table, like this,
Yeah.
like in the slides, like let's draw this
Yeah.
table.
Yeah, just give up like a table and
So-
argue that, oh, actually the amortized cost for both using this potential function, both
It's
of
the
them,
same.
yeah, like give a O1. Even if it's different, it doesn't really matter. Like if this
Okay.
was 3, right, if this was 4, well, both of them is upper bounded by O1.
Alright.
It's a concern, however, if the shrinking one, you get like n instead of 2. that means like your argument doesn't really go through well, because like
Oh, okay.
sometimes you say the amortized cost is constant, sometimes you say it's linear in n. So that's bad. But if you choose a good potential function that satisfies all the conditions that we need, we know that amortized cost for them is 2 and 2. And then as long as all your potential function satisfies this condition, phi 0 equals 0, initial state has 0 potential, and then for every potential it's always greater than equals to 0,
Okay.
then that's fine.
Okay.
Because the main reason why it all works is because of this math that I went through it before. So using that condition, all this math checks out. So you don't have to show this math in exam, of course. I'm just showing how it works.
I saw this in slide, right? This one I actually understand. What I want to see was how that so we show this. Okay, I want to confirm something. So they said this phi delta phi I, right? It's like delta phi I is the potential difference at I, right?
Yep.
So is it for any operation?
Yes, for all operations. It's
So let's say
always-
I had a question like the previous question, question 3, like that's like a add, then you have like what was it? Was it DQ and Q? Yeah.
Yep.
Then so all these operations, like it can be like DQ or Q or anything, any operation that they give and you need to show that it works.
Yes. So you see here, right? I for every single one of them, for NQ, I argue this is the potential difference for NQ. It's 1.
Okay. So you
Then-
just go through, use the function and show that each of them all have like some.
Yes.
You show that the potential function works for all the functions, then it's okay already.
Yes. So here again, like I said before, the delta phi I for DQ is different, right? The potential difference for
Yeah,
DQ is different from even NQ. This is 1. This is -1.
Mhm.
Then for delete is different also. It's -k.
Okay.
For adding, it's also different. It's like size of A, right?
Yep.
So but the point is that at the end of the day, the amortized cost is always what we need. When you sum up the actual cost and the potential difference, okay, I should have a summary table, but I think it slipped my mind.
Yeah, that's fine. Just because I think the only thing like I really struggle with is like how to write this, how do I
Yeah.
phrase this argument like
Yes,
properly?
yes.
Because it's very easy to see, very easy to like recognize, not very easy. It's like it's okay it's just easy to see like the pattern.
Yes.
Like, okay, this function will work here, but then after that, like when you give you like all these operations, I'm not sure how to like formalize them into an argument that
Yes.
say like, okay, this is O1.
Yeah. So for potential method, as long as you fulfill the conditions, just trust it. So wait, let me just maybe show you like one of my past assignment questions. So one sec, let me search for it first. So really like how I did it last time. Second, yeah. Let me share screen. So I think I missed out one subtlety in this answer somewhere, but basically like for most part it was accepted. So this was one of my assignment questions. This is how I argue for accounting method. I just say, oh, insert is charged $2. So I didn't say the question, but I just want to show you like how I wrote the answers last time. So like I say, oh, instead of charge $2, $1 is used for like the actual thing, and $1 stored in the bank for future something, right? Then there's this replace sum operation. I say that, oh, it's actually free. I charge $0, right? This is a counting method.
Okay. Then you deduct from the banks or something like that. Okay.
Yes. Then here I argue for the potential method. Then I say, oh, the potential method is the length of the data structure after each operation. Then I argue, oh, it's a valid one because this is the state, right? Pi 0 is 0. Then, well, for all I, the number of elements is always non-negative. I argue that it fits the definition of potential method.
Okay.
Then I also argue, hey, for insert, here's the actual cost. And here's the potential difference, right? Do you see the potential difference here?
Yes, yes.
Yeah. Then I say, oh, so the amortized cost is summing them up. Summing them up. Same here. Actual cost is something, then removing is like this time. Amortized cost is this much. So therefore, the amortized cost of n operations is blah, 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 blah. So what's this? Yeah, so correct. Yeah,
Okay,
so this
okay.
was how I argued amortization for my assignment also last time. So for the most part, I think I was given marks. I think I got deducted somewhere because there's some subtlety that I missed out. But the point is that this structure of answering should be okay.
Okay. I think that's quite helpful. I
Nice.
just like the formalizing was a bit hard. I think
Yes.
the recent few lecture were like quite.
Yeah. Yeah,
okay.
that's the tricky part of amortization, right? Like it kind of makes sense. All makes sense, right? Expensive operation is charging. So amortization techniques is about trying to give you a bit more formalization, but we give you enough room to explore.
Yeah, it's also because like we've like kind of seen this before like, under
Yes.
our 2040s. So like okay, I think I get it. Okay, thank you.
No problem.
Bye bye. All the best for your midterms. Yes.
Thanks. I
Okay,
got one
bye.
more. Yep. Okay. Nice. All right. So that was amortization. I'll stop recording.